is Chapter 2, Section 9, Calculus, the derivative as a function. I'm your host, Dr. D. There we are. Okay, today is a seriously important lesson, and it's going to have ramifications all through the year. So this is not a lesson to shortcut. You might want to watch this over and over because it'll be an instant classic. So let's get started. Okay, like we talked about last lesson, the derivative of f of x at x equals a is going to be f prime of a, which is the limit as h approaches 0 of f of a plus h, that's f of a plus some h value further, minus f of a, so that's your difference in y's, over the difference in x's, which is h. Now, we're doing a minor change to it this lesson. That is, we're just making a general derivative of f of x with respect to x. So that's going to be f prime of x. That's the limit as h approaches 0 of f of x plus h minus f of x all over h. So this is a function now. The derivative is a function of the original function. Now, calculus was invented in the early 1700s, and in Western Europe it was done by Sir Isaac Newton, and his notation was f prime of x or y prime. Now, in Eastern Europe, a guy by the name of Leibniz also developed calculus, and his notation was dy dx or d dx of f of x. Now, where dy dx came from is the delta y over delta x, we take the limit as delta x approaches 0. So that means your delta y and your delta x become infinitesimally small, thereby signifying dy dx. And you say it dy dx. You don't say it dy over dx. You just say dy dx. Now, an interesting phenomenon is that most mathematicians use f prime of x, and most engineers use dy dx. So we need to be conversant both ways. Now, if you want to say f prime of a, then that's saying dy dx at x equals a, and that, after all, is what f prime of a is. It's the derivative of the function at some x equals a value, rather than just at a general x value. Okay, so let's do a couple examples. They're going to be really similar to what we did in section 8. And then we're going to go look at the derivative as a function, and that's going to have some implications into where a function can be differentiated. Yeah, I'm glad I used that word. Differentiate is the verb form that means to take a derivative. So derivative is the noun, differentiate is the verb. So I differentiate a function, which means I take the derivative of it. So, cruising onward. All right, first example, here's our function, f of x equals x cubed minus 2x squared plus x minus 3, and we want to find f prime of x. So, as usual, f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, do you think that could be a really important thing for you to memorize?
That's the smartest thing I've ever heard anyone say about anything.
Yes, it is important that you totally memorize that. Not that you're familiar with it, but that you could tell me this if I came to your house and woke you up out of a sound sleep at 3 in the morning. You could tell me what f prime of x is. Okay, so it's f of x plus h. Well, that means I have to take the function and put x plus h in for x. So there's my x cubed, x plus h cubed, minus 2x squared minus 2x plus h squared, plus x plus h, minus 3 minus 3. Now, minus the f of x, so minus x cubed minus 2x squared plus x minus 3, all divided by h. Remember, we're writing the limit statement before every single step until we actually evaluate the limit. Okay, so next step. Okay, we have to remember how to expand a cubic. Well, good thing you guys had an excellent Algebra 2 teacher. So x plus h quantity cubed is x cubed plus 3 x squared h plus 3 xh squared plus h cubed. Remember how that worked? The x goes 3, 2, 1, 0. The h goes 0, 1, 2, 3. And the coefficients go 1, 3, 3, 1. So there's my x plus h cubed. Now, minus 2x plus h squared. So that's going to be minus, now it's x squared, so it's going to be minus 2x squared. Then plus 2xh, so it's going to be minus 4xh. Then plus h squared, so it's going to be minus 2h squared. Okay, now plus x plus h minus 3 minus x cubed plus 2x squared minus x plus 3. And I just barely made it in. All this is divided by h. Now, let's see what we can get rid of. Notice I have an x cubed and here's a minus x cubed. Bam, they're gone. Then I have a minus 2x squared. Here's a plus 2x squared. They're out of here. Then we have a minus 3 and a plus 3. Hasta la vista, baby. Okay, so that's all the things that we can just... Oh wait, or is it? Where did we get plus x plus h? Oh yeah, there's another one. We've got a plus x and we've got a minus x. Okay, now we really are finished. So, yeah, let's just crank this puppy on out now. So we've got the limit as h approaches 0. You know what we're going to do is cancel the h's as we go. So notice 3x squared h, the h's cancel there, so it's just going to be 3x squared. Now we've got 3xh squared. So 1h cancels, so this is going to be plus 3xh. Then we've got h cubed over h, which is going to be just h squared. Then we've got 4xh over h, so the h's cancel, it just becomes minus 4x. Then we've got minus 2h squared over h, so that's just going to be minus 2h. Then we've got plus h over h is going to be just plus 1. And that's it. Okay, so let's crank this puppy out now. We're ready to evaluate the limit as h approaches 0. So if h is going to approach 0, that means that term's gone because 3x times 0 is nothing. 0 squared is nothing. And 2 times 0 is nothing. So what do we have left? We've got that f prime of x equals the limit as h, I'm sorry, what the heck are we doing? We don't need the limit. We already evaluated the limit as h approaches 0. So f prime of x equals 3x squared minus 4x plus 1. 3x squared minus 4x plus 1. So, what you guys could do is take this to Mrs. Coley and ask her how to get f prime. She actually remembers. Okay, so check that out. See how good Mrs. Coley knows her calculus. All right, so cruising onward. Well, now, the thing I just want to say before we cruise onward is make sure that you can do this, because that's guaranteed to be on the Chapter 2 test. So, next challenge. We've got f of x equals the square root of 2x minus 1. And we want to find f prime of x for this. Okay, so now we've got f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. Standard. Okay, so what is f of x plus h? Well, we have to put an x plus h in for x. So it's square root of 2 times quantity x plus h minus 1. There's f of x plus h. Minus f of x, which is square root of 2x minus 1, all divided by h. Now remember, first thing you do to evaluate a limit is just put 0 in for h right now and see if it works. So you're going to have the square root of 2x minus 1 minus square root of 2x minus 1, which is 0 over 0, and it doesn't work. So we cruise onward. So now we need to get rid of the radicals on top so we can cancel h's. So the way we do that is by multiplying by the conjugate. So we're going to just skip a step and multiply by the conjugate right here. So we've got the square root of 2 times x plus h plus 1, rats. Minus 1. Now instead of minus, we're going plus square root of 2x minus 1 over the same thing. So I basically multiplied this thing by 1 because I have the same thing on top and bottom. All right, now notice on top I have a minus b times a plus b. So that equals a squared, which is 2 times x plus h minus 1. There's my a squared, minus b squared. All over this mess that we created for ourselves in the denominator. So I have h times the quantity square root of 2x plus h minus 1 plus 2x minus 1. All right, so now notice what we have on top is 2x, well, let's just distribute it out. All right, so we have 2x plus 2h minus 1 minus 2x minus a minus 1, which is plus 1, all over the denominator. All right, so look what happens on top. 2x minus 2x, they're gone. Minus 1 plus 1, they're gone. The only thing we have left is 2h on top. And so notice 2h on top and h on the bottom means I can cancel, and I'm left with the limit as h approaches 0 of, okay, remember, that 2x are gone, that 1's gone, and then the h and h here are gone. So all we have is 2 over the square root of 2 times x plus h minus 1 plus root of 2x minus 1. All right, so as in every one of these limit problems, the key thing is you have to get h canceled between the top and the bottom. Well, now once we have h canceled, we don't have 0 over 0 anymore. We've got 2 over 2x, square root of 2x minus 1, plus square root of 2x minus 1. So what's that equal? Well, when we put in the 0 for h, we've got 2 over square root of, this is just 2x minus 1. And then we have plus another square root of 2x minus 1. So basically what this equals is 2 over 2 times the square root of 2x minus 1. Notice square root of 2x minus 1 plus square root of 2x minus 1 is 2 square root of 2x minus 1s. Now the two 2's cancel, and we have our final answer, f prime of x equals 1 over the square root of 2x minus 1. Now you might find that Mrs. Coley has forgotten how to do that. She's good with polynomials, but you give her a radical or a fraction and it gets a little sketchy. See how good you guys do after, I won't say how many years it's been, but first year I taught calculus was 2002, and the last year I actually had calculus myself as a student was 1977. So 25 years of not using it, you definitely lose it. But I've got it back. So here we go. Let's on to the next challenge. Okay, we've been saying that f prime of x is the derivative of f of x at any point. And what's the derivative? It's the slope at any point. So here's what's going on. We've got a function f of x. We don't even have an equation for it. We just have this graph of f of x. Now, we're going to make a graph of f prime of x that's going to correspond point by point with f of x. Now, the key thing is, the graph down below is going to be the slope of the graph up above. So, let's first identify some easy points. What are easy slopes of this blue curve? Well, the top of the mountain the maximum, the relative maximum, is going to have a slope of 0. So that's one place guaranteed. If I take this point right here as a slope of 0, then right down here, my value for f prime of x is exactly 0. Same thing here. I've got a slope of 0 right here. So that means right at that x value, my derivative is 0. Okay, likewise, let's just do all the rest of the maximums and mins. So there's a slope of 0. Hard to do it with the shadow getting in the way. All right. So those are always the first points you want to put on your derivative graph, is the easy ones. Now, the next points, we'll do the beginning point. Where should this go right here? Well, remember, f prime is the slope of f. That means you just look at this and say, approximately what's the slope of this blue curve right at the bottom? And I think you would say that it's somewhere between 2 and 3. So it's a little steeper than 2, but it may not be as steep as 3. So let's just put our red point right at 2.5. Now the question is, as we go up this curve, is the slope getting larger or is it getting smaller? Right, it's getting smaller. It's getting less and less steep as I go up. Now, the next question is it positive or negative? Well, clearly it stays positive all the way to here. So that means the slope is going to be going down, getting less steep, but it's still positive. It's still above the x-axis. Now, one more thing. Is the slope changing a lot at first or a little at first? Yeah, I think you'll notice the slope doesn't change very much between here and here. It's pretty much constant. And then when it gets to about here, it starts to change faster. Okay, so what we have is the slope stays a little bit the same, and then it starts to drop. Now, same thing when it gets to here, it's changing rapidly right in here. So, you know what, I leveled off a little too soon. Okay, it's changing rapidly. Now notice the curve, the slope here is negative. And it's getting more and more negative. Now, let's look at one more thing. If this is a ski slope and we're going down the hill, it's getting steeper and steeper and steeper, and right about here, it's beginning to level off. It's beginning to not get steeper and steeper anymore. This is called a point of inflection right here, and I'd say it's right about there. So my point of inflection is going to be another important point. That's going to be the point of maximum downhill steepness. Now, what is the slope right about here? Well, I'd say that looks like about -3. Okay, so that means what we just said is the steepest the blue curve gets in the negative direction is -3. Now, once it passes -3, it's still negative, but it's getting smaller and smaller negative numbers till it goes up to 0. So we basically have the situation where it's going like this. Now, at this point, and let's fix that a little. Okay. Now at this point, the slope is beginning to go positive again. And it's very small positive, but it's changing pretty quickly. And where is the point of maximum steepness? It's as steep as it's going to get, right about here again. And so we have another point of inflection right about here. Now what's the slope right here? Well, that's just maybe 1, maybe slightly bigger than 1. Because notice, this is super steep, so it's going up as high as 2.5, almost 3. And this is also really steep going downhill, so it's going down to -3. But now when we're going up, it's only going up as steep as 1. So my slope curve here really only maxes out at about 1. And then it's going to go back down to 0. Now what does it do? Well, it's going back negative again. So that means our slope is negative. Now where's the steepest downhill? Here. The steepest downhill, it's getting steeper and steeper until right about here. Let's see. Yeah, right about there. That's about as steep downhill as it's getting. And then it's still going downhill, but it's getting shallower and shallower. Now, what is this slope? It looks like about -2/3. Not quite. It's less than, it's greater than -1. So it's just slightly negative. But it's not all the way to -1, notice. So we're leveling this out right there. Now, hold on.